I'm going to try to keep this fast. Number 2 and number 11, they were temporary supports as we've seen here. Now, I've got a lot of thoughts on everything, but these are just shear walls, I'm thinking, while the transportation and while the bridge is being put in play. They're acting as shear walls to keep the bridge from racking. Right here and right here. Okay, so if that's a shear wall, we can get hinging here, the crack. And that would, remember we were talking about a crack that the engineers are supposed to have found and spent forever talking about it? Perhaps this thing started racking. They do have an umbrella as a canopy. I've got so many things that I find wrong with these bridges. You know, I said in the 2016 drawings, and that's all we had, that I'm the only guy that was out there complaining that the canopy didn't have enough structural support. And sure enough, it appears that Louis Berger came along and corrected, if you will, Denny's plans and made them put 2 additional post-tendon longitudinal members in. So I think these are shear walls, and after the bridge is finished, this shear cabling can be removed. It's kind of simple as that. Let me say a couple other things too. The 1, 2, 3, 1, 2. Notice that, what I just did. This is the change of direction of forces in this bridge. Between these two right here, number 6 and number 7, forces are changing directions. They're going this way, direction to the left and then direction to the right. As you can see here, between number 8 and 9, this member 9 is forcing directions off to the right, and number 10 is forcing directions into the pylon section, and then number 2 is a forcing direction into the abutment. Now this may look like a crazy angle. Let's address that. The loads applied, the forces are between these two are forcing, between this and this, are forcing this direction on the, from this guy, number 4. When the force is applied here, this is on a slight angle, which forces are driven down, and it's being on an angle, it's going to drive it that way. Imagine this as a spring. Imagine a bottom deck as just a spring, a long coiled spring. And as you put forces on it, imagine how you're pushing away. Now this is the one that's kind of, you know, it has me. It's not quite 90 degrees, but it's pretty close there. And these forces coming down, this does have me. They come down, they hit here. This is driving still, but this force driving down, I think it was resolved somehow, obviously, or I don't know. But this would be a weak point as far as I'm concerned. And also, as you know, the truss being down the center of the bridge, I think is just, a concrete bridge is just ridiculous with the loads that are being applied reversely from the bottom deck and also from the dead load from the canopy umbrella from the top deck. When I say reversely, so let's say this is an I-beam. An I-beam, you can go 2 things. I-beam, this bottom plate, if you will, has transverse, has longitudinal post-tension cables in it. I think by itself, it's capable of holding itself by itself. And then the same with the canopy, ideally, it's capable of holding itself. So these two will be parallel from each other without any uprights needing to play along at all. Just done, none. So that would be ideal with no sagging in the middle at all. And that would, because it would be looking for the middle because there's nothing there. So no sagging. And then you add your truss to transfer the loads and create rigidity between the top plate, the canopy, the slash umbrella. So and the bottom plate, they're tied together using these post-tension rods because we've got, in building this bridge, we've got joints here, we've got joints here, we've got a joint between the blister bar and the top of the umbrella, the canopy. That's just inherently creating weak points, slip joints. It's just so the forces come down. This has a shear factor it's got to deal with as the forces are loaded from the pylons, 16-inch pipes, creating a dead load on top of each one of these blisters that also has to be resolved. Again, as those forces come across, they have to be resolved. This is, this would be under shear loading, shear forces at that point. All of it would be. Okay, this is the one that's my really iffy one, bone of contention. And of course, I hope they did some crazy scale model of this 30, 50 feet big and played with it. I just don't know, you know, why didn't they brag about it? FIU is a structural engineering college. They just put their hands all on this. I don't think they got out of not putting their hands on it. So this, I think, is just shear bracing, and you can remove it after the fact. So the load comes down between these two. The load pushes over to the right. It's resolved by the abutment, the pylons, and the other bridge being abutted to it. I want to scroll down and show you one more thing here. This is the bottom of the other bridge, and this would be the cantilever for where the elevator, etc. is. And we see the pylons are going this direction, so that's where it would wind up at that point with the structure. And again, some of these are just designed to hold the bridge together as it takes wind and forces and direction of all the forces. Now let's go on, and I'm not going to be too specific. This is about the 4th time I've attempted this video, so I'm trying to refine it down to something real fast. And I'll end it with the blister bar and the loads and the other possible common defect that could show itself. Here are the connections. This would be the forces coming down, sliding also. This would create a shear moment. Actually, in the blister bar, in the post-tension member itself, and I say member, I mean the literal bar, as it's being driven, and it would be at the connections also, where they're being driven, where they come across anything stationary, the concrete, especially during wind and movement. They're going to have a lot of vibration and racking going on. Okay, sliding down, and this does have connections for that supposedly. Here are the blister bar. The blister bar, some of them line up perfectly, and this would be this one lining up, well, ideally in the center, over top of the two supporting members. Now, all bets are off if this bridge was capable with the longitudinal post-tension cables, able to take the entire load of the 16-inch pipes. I don't know if that's possible, if that was possible with this design. So the load comes down, and if the blister bar is separate also, if it could be made as one, that is structurally sound, like a steel plate, if you will, just like this steel plate here of the 16-inch pipe. If it could be made that if you push down on this blister bar acts as one, well, then the forces come out here. The load of this comes out to each end of the blister bar. This is a 12-inch deck, so that comes out to the 8,500 psi decking along with the reinforcement that's in that decking. With that said, it also has to be driven down as one, and that would then transfer the load onto these columns equally, but offset nevertheless, because this is not in the center of, ideally, the crisscross area of this, where these two meet. So you do have a cantilever effect going on, action going on here, which is another point of tension being created right under here. And ultimately, these forces have to be canceled out with the supporting member, which would be another shear force, a shear point, if you will. And that's it. That's all load paths. All right, I'm canceling this video out. Hope it was short, because I don't know the time. I can't see it running time. And jump in. I know I left out quite a few things. I did this video 5 times, 4 times, whatever it was, and I just wanted to get it down. And thanks for watching. And you guys are, your comments are very, very interesting.